at the end of the lecture. I'm hoping, and again, I apologize for the delay, I'm hoping homework 6 grading would be done by today. Are there any questions on logistics? Tyler?
The time's still taking a while, but what's grading for the, have you started grading for the mini projects?
No. Unfortunately, so, well, no, not the best way to start the sentence. So I will be inviting the top 10 submissions to present on last day of class. I might not be able to give that long of advance notice, so it might be just like 1 week before telling them you do it. I'll try to get it done. Let's see. I don't want to make any promises because I know I most probably won't be able to keep it, but I'll try to get it done by the end of the Thanksgiving break, hopefully. Mark?
Do the top 10 have to present, or can they?
No, it's optional. But if the top 10 don't present, it doesn't trickle down. So if you're 11th and the first one says we don't want to do it, you still don't get to present. Any other questions? I already posted on CS Ed Week is our last day of class. In particular, there would be a demo competition. You guys must have gotten emails on November 30th. So if you have a demo that you think you can show to school kids, I highly encourage you to take part in that competition. If you are thinking of applying to grad school, please do consider applying to the Senior Scholar Program. You don't have to apply to UB to get some money, but you get more money if you apply and join. So, but for example, if you're a senior and you're applying for grad school and you're already planning to work with a faculty member in spring anyways, might as well just do it. Just get some extra money. All right. Again, please ask questions. So I talked about in more length in my response, but as I've said many times, when I say, do you guys have any questions? And you guys don't ask any questions, I really do not know. As one of you pointed out, this is the 9th time I'm teaching this course. I've done these proofs multiple times. By this point of time, they all seem obvious to me, right? So when I'm asking, do you guys have any questions? And you keep quiet, I'm like, okay, it's obvious, let's move on, right? But when I look at the feedback and then it's like, well, I don't quite see what's going on. I mean, things are going too fast. So please do ask. I do understand that sometimes you might feel uncomfortable, maybe because you think you're slowing down the class, but that is not your problem, right? So, I mean, your job here is to come and make sure you understand what I'm saying. If you don't, you tell me. If for whatever reason I think we are going off track, I'll tell you, but that's not your job to decide. Okay, that makes sense? Okay, thank you. All right, so we were looking at the weighted interval scheduling problem. So to remind you, so this is a generalization of the interval scheduling problem that we had done near the midterm. And now you have n jobs or n intervals, each has a fixed start time, fixed finish time, but now it also has a value. So if you pick the ith job, you get a value of VI. Think of it as maybe a profit or points or whatever. And your goal is to output a schedule, which is a subset of jobs so that no two jobs conflict with each other. Right? So if you draw out two intervals, they should not overlap. And your goal among all such valid schedules is to find one that maximizes the value of the entire schedule, which is just defined as, oh, bad typo, this should be sum in J. So you sum up the values of all jobs that you picked, add up the values, and that should overlap. And we will assume that in the input that's given to us, the jobs are already sorted by the finish time. If not, as usual, we can pay an extra and log in time and get this assumption to be true. A couple of more definitions. Once we have assumed everything sorted by the finish time for any job J, so let's say this is my job J, you figure out the largest job that does not conflict. So you keep on looking forward in terms of finish time. As long as they don't conflict, you're good, right? So find the largest value of I that's strictly smaller than J that does not overlap. And it is possible that there might not exist such an I. For example, if J is the very first job, then there's nothing before it. So in such a case, or maybe you're looking at the second job, but it conflicts with the first job. And so in that case, the value should be defined to be 0. And we're also going to use opt of j to denote the optimal value of a schedule on the instance from 1 to j. When I say instance 1 to j, I mean you look at the input jobs that are the first j input jobs. And in general, we are interested in opt of n because that's our entire input. But I forgot to mention, we're going to make a simplifying assumption, and instead of trying to compute the optimal schedule, we're just going to try to compute the maximum value that you can get. And we'll see shortly that just knowing all the values of all the optimal values from opt1 to opt_n is enough to recreate the schedule. So this is kind of analogous to Dijkstra's algorithm, where the algorithm itself just stated in terms of computing the shortest distance, but if you were careful and kept track of kind of the shortest path tree, then you could actually also compute the shortest path. And in general, this is a useful trick in many cases. When you're designing algorithms, when you have to compute an object that has a certain optimal value, it sometimes is easiest just to try to compute the optimal value itself first. And in many cases, not always, once you have that algorithm, you can generally modify to actually get that object itself. All right, so first thing to note is P of j has to be strictly smaller than j because it's the index strictly smaller than I. And this is the property we derived last time. This is the recurrence relation for optimal values that we're going to use. This is true for all j. So opt of j, and we looked at two cases. Either the last, so again, remember this is the instance from 1 to j. Either the last job is in the schedule, in which case you get a value of vj from that job, and then basically you have to throw away everything that conflicts with j. And by definition of j, everything that conflicts with j is p of j plus 1 all the way up to j minus 1. Okay? In other words, if you pick j, the remaining instance is 1 to p of j. So that's why you apply opt of p of j over here. If on the other hand, j is not in the optimal solution, then the solution that you had to begin with is also an optimal for j minus 1. And since these are the only two cases, the actual value of opt of j is max of these two. And so we talked about this briefly last time, so I'll quickly go over it again. And so here, this is exactly what I was saying earlier. If you do know all the opt values, opt of 1 all the way up to opt of j minus 1, there's a very simple check that you can perform to figure out whether j is in the optimal solution from 1 to j or not. Okay. In particular, you just look at these two values, and again, I can compute all of these because I know v of j from the input, and since p of j is strictly smaller of j, opt of pj is one of these values. So I can compute this value, and obviously opt of j minus 1 I also know. And if the first argument is strictly bigger than the last, then it has to mean that j is in the optimal solution. If the second argument is strictly bigger than the first, then j is not in the optimal solution. If they are the same, then you have two optimal solutions, one of which has j and one of which does not. Okay. And later today, we'll see how you can just basically use this observation recursively to compute the actual optimal schedule. Mark.
Do you have to store the opt values somewhere?
Yeah, so we will store all the opt values somewhere. Yeah, you do need to know all of them to figure this out. All right, questions? Okay. So once we have this recurrence or recursion or a recursive formulation of the optimal, the obvious thing to do is just to implement the recursion as is. Right? So this is it. So it's compute opt. If j is equal to 0, so I didn't mention the base case of this is opt of j is 0 because you don't have any interval, so you don't get any value whatsoever. And if it is 0, then return 0. Otherwise, you basically just replace opt by compute of opt, and that's it. Okay? And you can very easily prove that this is correct by induction. You do induction on J. Base case is correct because in this case you're outputting 0. Otherwise, by inductive hypothesis, you assume that compute opt of P of J is exactly equal to opt of P of J, and compute opt of J1 is exactly equal to opt of J1. And then by the correctness of this recurrence relation, you get correctness for, so by inductive hypothesis, you get these two are equal, and then since we have already argued this recurrence, this argues the correctness of the algorithm. Are there any questions before we go on? Again, if you do, please do ask. Yeah, Mark.
How long does it take to compute P of J?
Good question. You can do it in n log n for sure. I leave it as a homework exercise, well, not as a homework assigned, like an exercise to do at home. There's a bonus problem. I actually do not know if you can do it in O of n. So if you do figure out that it can be done or figure out it cannot be done, please let me know. But you can definitely do it in n log n to compute all of P of J, given the input. Any other questions? Is everyone comfortable with the recurrence formula? And then this is essentially just implementing it. Okay. Do any of you see any issues? So this is correct. Do any of you see any issues with runtimes if we were just to implement this as is? Mehmet. It might not be exactly 2 to the n, but you can make it run in exponential time. And the main reason is if you just blind, okay, so let me give you an example. So here's an example. Here's an instance where everything's set up so that P of J is exactly J minus 2. Just, well, like, kind of, everything just conflicts with just the previous thing. And so if you look at, so let's just say opt of 5, right? So in this case, P of 5 is 3, and 5 minus 1 is 4. So you recursively called opt of 3 and opt of 4. So far, no harm done, everything looks good. P of 3 is 1, and so you run opt of 3, you get opt of 1 and opt of 2. Again, we are good, right? So far we're just computing new problems. Opt of 4 is opt of 2, right? So, So opt of 2 runs into opt of 1. You're like, well, this is the base case, maybe it doesn't matter that much. You can get away with it. You do opt of 4, you get opt of 2 and opt of 3 again. But the way the algorithm is stated, you just go ahead and do recursion again. Because just say, whenever you need to figure out the value, just recursively call it. And so on and so forth. Okay. So in particular, if you instead of only having it till n, if you instead of only having it for n equal to 5, if you had for general n, then the number of subproblems that you have to solve would be exponential. The base won't be 2. If you are familiar with Fibonacci numbers, then the number of problems you have to solve is the nth Fibonacci number. So it still grows pretty quickly. Okay. So, and this is the problem. Right? So the issue is you have a bunch of these subproblems or recursive calls that you're just kind of doing over and over again. Okay. Well, this is a classic case where you should use some space, right? If you have to if you are solving the same problem over and over again, don't resolve it, just store it in some place and just reuse it. Okay? And the important point to note here is, even though in general you can have exponentially many recursive calls, you really only have n plus 1 values, right? Opt of 0 up till opt of n, that's all you need to compute. So you're really doing lots of extra work that you should not. Questions? Is everyone okay that if you're not careful, you'll take exponential time? Okay. So now that you have turned in your homeworks for 8, question 2, the basic insight for question 2 on homework 8 is exactly the insight in general for dynamic programming. So this was computing power of a raised to n. if you were to solve this recursively when you were not careful, and let's just assume n is even though it's not quite the case, you'll say return power of a comma n over 2 multiplied by power of a comma n over 2. If this is what you implement, your algorithm is going to run in linear time because you have n, 2n over 2, n over 4, n over 4, n over 4, and so on and so forth. And so this is O of n. And the reason there's so much time is because you recompute, right? N over 2, n over 2, and so on. And so the idea is don't recompute, right? So call power of a comma n over 2 once, store it, and just reuse it. And so you do n over 2, n over 4, n over 8, and you're only doing log n of these. Okay? And so that you only need to compute once, and this is log n. Right? This is a much more dramatic change than we generally see for dynamic program because here you're just using kind of maybe one variable, right? So that's like only constant amount of space. Typically in dynamic programming, you need to spend more space, but the idea again is you should not recompute a value or a subproblem if you've already done so. And that is the main difference from maybe divide and conquer and dynamic programming or just doing a kind of naive recursive algorithm. All right, any questions so far? Tyler.
Isn't this called memorization?
Exactly, thank you. So there's a technical term for this, it's called memorization, using memory to do good things. And we'll explicitly talk about it soon, but yeah. Any other questions or comments? All right, so we already talked about this. For this problem, you have n plus 1 distinct opt values, right? So opt of 0, opt of 1, opt of 2, all the way up to opt of n. Okay. And so in the previous case, we essentially only needed one variable, but in this case, we just need an array to keep track of all of these opt values as as was asked earlier. So here's the basic idea. So we're still going to have a recursive algorithm, but we have a global array M where we store the values of all. So M of j, once the algorithm is done, will store the value opt of j. So the base case is again similar. If j is 0, you just return 0. If your recursive call is asking you to compute opt of j, and M of j already has a value, that is, it's already been computed, you don't do a recursive call, you just return that value. Okay. Otherwise, if it's not computed, that's when you do recursion and try to figure this out. Okay. So again, the idea is, whenever you want the value of opt of j, you first check whether it has been computed. If it is, just reuse the value. If it has not, only then apply your recursive calls. Okay. And again, using recursion, you can argue, using induction, you can argue that this algorithm is correct. Again, what this is doing is just, again, implemented that recursion that we had derived earlier, but now using these values of that are stored in M. So in this case, basically the only time you're doing anything is when you have a recursive call, and if you have a recursive call, you're only doing constant amounts of work. And so then the runtime then totally just depends on the number of recursive calls that you have. And then the question is, how many recursive calls can you have? Well, the only time you're going to make a recursive call is if the corresponding value, like you have a recursive call for j, if M of j is not null. Is null. So you're going to have at most one recursive call per each entry in your array. And you have n such entries, so you're going to have at most n recursive calls. And so this implies this algorithm right, so whenever you have recursive call, a value is assigned from null to a specific value. And this can happen at most n times. And so this gives an O of n time runtime. So we have gone down from an algorithm whose runtime could be at least exponential in the worst case to something that's linear. Okay, and so that's a big saving. And all you had to do was use O(n) amount of space to do this. So maybe talk to your friends for half a minute. Let me know if you have any questions. If not, there's actually another version of this, which is an iterative version, which tends to be slightly easier to grasp. So that's what we're going to go with next. All right, are there any questions? Tyler.
So it's always makes all that login, you should all that to do.
Right, so if your input is not sorted in the finish time, or overall runtime is unlogged because you have to sort. But if it's already sorted by finish time, it's O(n). Actually, sorry, no. So you also have to compute the p-values. And that I do not know how to do better than n-log(n). So you're right, n-log(n). So this is O(n) assuming inputs are sorted by finish time and you have the p-values computed.
So
If it's not sorted, then you still have to pay n-log(n). So yeah. Yeah. Any other questions? All right, so what we're going to do next is come up with an iterative version of this algorithm. And I don't want to go into the debate of whether recursion is better or iteration. We leave that for other classes, I guess. But the reason why we're going for the iterative version is, in general, when designing divide and conquer algorithms, the iterative version of divide and conquer tends to be easier to do. Okay, so in this case, that's not quite true, not necessarily true, but it's easier to design, and not only is it easier to design, it also helps you kind of guide how you kind of develop your dynamic program also. Okay. So one property of opt of j in this case is to note that to compute the value of opt of j, you only need to compute the previous j-1 values. Right, so that's what we use, or that just follows from the definition of the recursion, which then suggests a natural iterative thing, right? So you start compute opt of 0, which you know is 0. Then opt of 1, that only depends on opt of 0, but you already know that. Opt of 2 can depend on 1 or 0, but you already know that. In particular, if you compute the opt values in order, by the time you want to compute opt of j, you would have all the previous value pre-computed. And so then it's just a simple iterative algorithm, right? So again, let's just say we're storing everything in M. M of 0 is 0. And then you just run your loop from 1 to n. And M of j, you just plug in the value, just use the recursive formula. But now note that to get opt of p of j, you just need to look up m of p of j. And to compute opt of j minus 1, you just need to look up m of j minus 1. Okay? And in this case, the O of n runtime is even more obvious. It's a simple for loop, and you're just doing constant amount of work. Okay. So what I'm going to do next is actually run this algorithm on a specific input just to make sure everyone's on the same page. And then we'll quickly see how, given all the opt values, you can actually compute the actual optimal schedule. Right? So again, remember, here we're just computing the value of the optimal schedule, not the schedule itself. Okay. But any questions? We move on. All right. Oh, sorry.
Are you going to show us how we compute P of J?
No, so I said that's an exercise to do.
So we won't need to code this for homework?
That I don't know. Or I won't say rather. You'll find out when the appropriate homework turns around. But I do have a story of P of J, which is the first time I taught this course, I thought I had a O of n time algorithm, and I actually gave it on the final. And yeah, it didn't go well. So I still don't know. I mean, every year when I teach this algorithm, I think I should sit down and think about it and try to figure out the runtime, and then just get lazy and I forget. And then I remember next time I'm teaching it. So it's a fun exercise. N log n is not that hard. You have to do some sorting to figure it out. But beating n log n is somewhat non-trivial, I think. So yeah.
When you say n log n is to compute all values of p?
The n log n is to compute all values of p. Yeah. So given the input si, fi, and vi, well, you don't know vi. You only need si and fi to compute all values of p. Yeah. Any other questions? Okay, so let's run this iterative algorithm on an example. And so it turns out in dynamic programming, in general, we'll have, in this case, we only have n plus 1 subproblems. In general, you have polynomially many subproblems. And the generally easiest way to figure out how this runs is to draw a matrix on an array and just walk through and fill in all the values. So that's what I'm going to do. I will just walk through and how you fill in these m, these entries in the M matrix on this specific input. Okay. So before I go ahead, as we already talked about, so as an exercise, so you can pj values can be computed in order n log n time. And if you are looking for a problem to think about, try to see if you can solve this in order. You obviously cannot do better than order n because you have to output n values. So, okay. So the important part to remember about the iterative algorithm is basically this formula that we use over and over again. So m of j is max of v of j plus m of pj m of j minus 1, and we initialize m of 0 to be 0. So let's look at an example with n equal to 5, and this is pretty much at least the relative orders of various things is what is the example that we started off with when we're trying to design the dynamic programming. So again, remember we're assuming everything sorted by finish time. So let's say the last guy has a value of 15. The fourth job has a value of 5. The third job has a value of 13. The second job has a value of 9, and the first job has a value of 10. Okay. So let's quickly compute the p-values. So what should p of 5 be? Uh, 5 actually conflicts with 2. 1. Right, so this. Oh, I'm sorry. You're right. Sorry?
Are we going to sort them by bench?
They are. So actually, yeah, I just made a mistake. Like the indices are in sorted order.
Yeah.
Yeah. So P of 5 is 2. P of 4 is 1. P of 3, 1. P of 2, 0. And P of 1, 0. Okay. All right, so we now know the p-values. We now know all the values of the jobs. And so what we're going to do is basically just compute the m values with this recurrence one step at a time. Okay, so here's our M matrix. So 0, 1, 2, 3, 4, and 5. So this is my matrix, and the indices here are the J values. So the initial step is to just set M of 0 to 0. So that's fairly simple. Now let's look at j equal to 1. So I'll apply this formula for j equal to 1. So m of 1 is max, sorry, this is 0, max of v1 plus p of 1 is 0. So that's m of 0, comma j minus 1 in this case is 0. So m of 0. So that's max of 10 plus 0, comma 0, which is 10. So we put in a value of 10 here. All right. Hopefully you guys have the p-values written down somewhere because they're going to go outside your screen soon. And so now let's look at what happens for j equal to 2. And this is where things start getting a bit more interesting. So you have m of 2 is max, so m of 0 is still 0, m of 1 is still 10. I mean, they never change because we're going iteratively and computing the m values. So this is v of 2 plus m of 0 because p of 2 is 0. And j minus 1 in this case is 1, so m of 1. So this is max of, so in particular, m of 2 depends on, j equal to 2 depends on j equal to 1 as well as j equal to 0. So this is p of 2 and this is 2 minus 1. So v2 is 9, so 9 plus m0 which is 0, comma m1 which is 10, which is 10. So we put in the value 10 here. Okay. Do you guys want me to keep on going? I can do it, or we can stop. How many of you want to continue and finish off the array? How many of you don't want to continue? That's what I thought. All right. Okay, so let's do j equal to 3. So you have 0, 10, 10. M of 3 is max of V3 plus P3 is 1. So that's M of 1. M of 2. So that's max of V3 is 13 plus M of 1 is 10 and M of 2 is also 10. So the first quantity is the larger one, so you get 23. So let's do j equal to 4. So again 0, 10, 10, 23. M of 4 is max of V of 4 plus P of 4 is 1. So M of 1, comma M of 3, which is max V4 in this case was 5, M1 is 10, M3 is 23, so this is 23. And finally, we'll do it for j equal to 5. So again, 0, 10, 10, 23, 23. And M of 5 is max of V5. P5 is 2. So it's V5 plus M of 2 and M of 4. V5 is 15. M of 2 is 10. M of 4 is 23. So that's 25. And so that's it. So this is the final. So this is the max value that you can get from any valid schedule on this impedance. Okay. So talk to your friends for half a minute, a minute. Let me know if any questions. If not, we'll go to the next step of, all right, now that I know all of these M values, how do you compute the actual schedule from this? All right, are there any questions? Mark.
Does this still work for negative weights?
Mark's question is, does it still work for negative weights? Yes. Basically, you can throw away negative weights. It's never going to help you because just adding up these match. But yeah, everything that we did, even if you didn't throw them out, would still work. Good question. Any other questions? Okay, so now let's look at trying to compute the actual optimal schedule from these opt values. So we'll first do it for the specific example, and then once you see one example, the general algorithm is fairly simple after that, but we'll kind of write that down explicitly too. Okay? And so once you have the opt values, the way you compute the actual optimal schedule is essentially the same thought process that we went to when we came up with the recursion. In particular, we start from n and move backwards. So we start off with the last guy. So in this case, we'll start off with 5. And the first question we ask is 5 in the optimal solution, or is 5 in an optimal solution or not? Right? So what we want to now do is compute an optimal schedule. Actually, in this case, it turns out there is a unique optimal schedule. And so the first question we asked, like we did when we're trying to derive the recurrence, is the last guy in the optimal solution? Right? Is 5 in the optimal solution? And remember, the way we do this is we look at the expression for opt of 5, which in this case m of 5. We have these two terms. And we see which one is bigger. If the first one is bigger, then 5 is in the optimal solution. If the second one is bigger, then 5 is not in the optimal solution. So in this case, the first term, which is 15 plus 10, is strictly bigger than 23. So that implies 5 is indeed in the optimal solution. Okay? So in my optimal solution, I'll definitely have 5. Okay? And so then we basically do the same thing as before. So when I say before, I mean when we're trying to derive the recurrence. The idea is if you pick, so again, in general, what we're saying is we look at this guy, see whether if this guy is bigger, then we recursively go back to the size p of j. Otherwise, we are going back to size j minus 1. Right? So in this case, p of 5 is 2. So we now consider the optimal solution without 5, which we had earlier argued is actually the optimal solution for 2. By the way, a reminder that O of 5 means this is the an optimal solution for the input instances from 1 to 5. O of 2 means it's an optimal solution for 1 and 2. Okay. And so in this case, I'm looking at the input instances from 1 and 2. Right? And so again, we now are at the input instances 1 and 2, and we want to ask the question, is 2 in the optimal solution or not? Okay. So the question we want to ask is 2 in O2? And so for that, we go look back at M2, and we look at the two cases, right? So if the first parameter was bigger, then 2 is in there. If the second parameter is bigger, then 2 is not there. Right? So as 9 plus 0 is strictly smaller than 10, this implies 2 is not in the optimal solution. Okay. So what this means is we now go back to the problem instance on 2 minus 1, which is 1 in this case. Okay. So now consider O of 1, which is, oh, sorry. So in this case, since 2 is not in the optimal solution for 1 and 2, that means it's actually an optimal solution for 1. And so in this case, we want to check whether 1 is in the optimal solution. Now, if your input size is only 1, it trivially has to be there because you always pick it. But let's kind of walk through this again. So the first term here is 10, the second term is 0, so the first one is strictly bigger, so 1 has to be in here. Okay. So as 10 plus 0 is strictly bigger than 0, that implies 1 is in the optimal solution. So what all of this means is the optimal schedule is to just pick 1 and 5. Okay. What I'll do quickly is actually, so essentially the idea is you start from the last guy, check whether in the, when you were computing m of n, whether the first term was strictly bigger than the second term. Right? If it's the first term, then n is in the optimal solution, and then you recurse on the input instance from 1 to p of n. Otherwise, you recurse on 1 to n minus 1. Okay? And so you can write this down as an algorithm. So if I call this algorithm m schedule, which takes as input n, all the computed opt values in m and all the p values in p. If n is 0, then you return the empty set because there's nothing going on. Otherwise, you check whether this term is strictly bigger than this term or not. So if v of n plus m of pn is strictly bigger than m of n minus 1, then you know that n is in the optimal solution. So this is the singleton set just containing m. And you should add to it whatever is the optimal solution from 1 to p of n. Okay. So m schedule p of n mp. Otherwise, you just return the optimal schedule for the first n minus 1 jobs. And so that's it. Right? So you just start up from the end. You basically use this simple check to decide whether for a given opt j, whether j is in opt of j or not, and then you just recursively do it. And this, you can, if you just think about it for a bit, you can show that this runs in linear time. So once you've computed all the opt values in linear time, you can compute the actual optimal schedule. And here are the homework solutions.